Continuing with chapter 6, we're going to start talking about quantum mechanics.
All right, so the reason why we talked about light is because historically, and really, this was used to figure out what was going on with atoms, because we know that there's this quantization. There's this special idea that we only have photons of light. And so when you take an atom and you heat it up, you get colors that come out of it. And you don't just get any colors, you get unique and consistent colors. So for example, lithium here we can see is always red. It's a particular type of red, a particular brightness. It's kind of a little darker, more orangey than the pinkish red of strontium. You get these characteristic colors. Some of them are really similar, like potassium, rubidium, and cesium all being really purplish. But there still is some variety. But importantly, every time you heat each atom, you'll get the same color out. And so while we may only see one color, what really comes out is an emission spectrum. So if remember we said spectrums were the ranges of all the possible colors. So when you heat, say, neon and you get the colors out, it may look like orange, but we can see that really it's a bunch of different wavelengths of light. But it is not continuous. It is only specific wavelengths. So you can see these sharp lines show up because those are the only lines, only wavelengths of light that are emitted. So if you remember, those are each color, each wavelength is a different color, and each color is a different photon with a specific energy. Okay, so when you heat up light, you heat up atoms, the energy that is emitted out via light is only particular quantities. It isn't just energy as a whole, it is particular types of photons that have unique wavelengths and therefore certain energies, right? Certain colors correspond to certain energies. You can see, hydrogen only has 4, but mercury, Hg has a little more. Neon has a bunch, right? So different atoms have all these different colors that come out. We only see one because your eye can't separate them all out. But you kind of get an average. You'll note neon is orange because there's a whole lot here in the orange part of the spectrum. Okay, so in order to explain this, right, why did atoms only emit certain things? We're kind of starting to look at some of the ideas like quantization, right? So we explained photons are quantized versions of light. So maybe the electrons around an atom are quantized. And what that would mean is that there are particular states, particular locations where we could find them. And the first idea was put together by Niels Bohr. And so what the Bohr model said is that the electrons orbited the nucleus in much the same way that a planet would orbit the sun, right? So you have, say, a ring that you could find an electron in that ring, or you could find the electron in this ring. Okay, and so you could find them in these different rings. And what that would mean is that those are particular places, particular locations, right? Kind of ring that electron can kind of move around in this ring, and it can kind of float around and come back on itself. But importantly, it couldn't move in between the rings, right? It was either in ring 1, 2, 3, 4, 5, whatever it is, but there's countable rings around the nucleus. And the electrons move around them like a planet, so he called them orbits. So this allows him, Bohr, to explain the lines of the colors of light that are emitted from the different atoms. And so what it says is, well, when you take an atom and you put it into some sort of energy source, like say fire, you excite the electrons. And so exciting means you take the electrons from a low energy state, like say the ground state, which is what they are outside of flame, say the lowest energy state, and they go up, right? They go up into these higher orbits, different orbits that are at a higher energy. And so they're all up in these high energy states. Well, eventually they lose the energy that they have, and those electrons relax. Okay? They relax, they go from these excited states when they're in the heat down back to where they were. Okay? And in order for them to relax, energy has to be emitted. So they could go, say, from this 3 state down back to the ground state. Okay? So they could go down, and that energy has to leave the atom. And the energy will be emitted as light. The energy will be emitted as light. And because the states are quantized, the electron had to go all the way from this energy to this energy, there's a particular difference in energy between those states, which means there's a particular type of photon that corresponds to that energy. Okay, so atoms have all these different potential states for their electrons. The electrons go in the flame, they go up, they come down, right? But that going down, that relaxation, always corresponds to the same difference in energy because the states are quantized. They're always the same. And what that means is that you always get the same colors of light that get emitted from the atoms. You have all these different states, so for example, hydrogen here, you have the different rings, 1, 2, 3, 4, 5, 6. This can just keep going, 7, 8, 9. Possibilities keep going, going, going. And so when they come back down, you have all these energy differences. And you can see when they come back down, you emit all these different types of light. And so people were just looking what they could see was the visible light. And so you can see with hydrogen, we get 4 lines that are in the visible light. There's a lot more lines, though, because there's a lot of other states that get all these transmissions. So if you look in the UV, you can see some out there. And then in the infrared, there are also some lines that show up there. So when you're heating up these atoms, they're emitting wavelengths of light, photons, in all sorts of different regions of the spectrum, just because they have all these different energy differences between all the different states. So that's great, but the Bohr model isn't perfect. It doesn't explain why there's any quantization. It just says, hey, if there's quantization, we can make something work. And so we need to do a little bit more, get a little bit weirder. And so we've already borrowed from photons, light photons. We already borrowed the idea of quantization. The other piece of the puzzle for explaining quantum mechanics is to explain the idea, to take the idea that light had both kind of those particle and waves. Electrons we think of as particles, maybe they're also waves. And so electrons behave as what are called standing waves. So a standing wave, that word standing implies not moving. So waves in water, like at the beach, those are moving waves. A standing wave is a wave that is still. So that would be something like this top description, where it's not moving because this point is locked into place and this point is locked into place. So a vibrating string, for example. And so now the wave goes up and down, up and down, up and down. And more importantly, it comes back and hits back at where it started. The bottom wave is not standing, right? It goes up and down, up and down, up and down, up and just down, and it stays. If this wave were to oscillate, this point would be moving up and down on this point, right? It'd be moving up and down. It's not locked into place down at the origin. Okay? And so this idea of standing waves, so a vibrating string only happens in standing waves because the points, like on a guitar string, the points are locked into place, right? You have here, and you can't move those points. The string is locked into place. And so the important thing is that when you have a standing wave, you have to lock in the number of wavelengths. It has to go up and down, and always come back as to where it started. So you have to have an integer number. So in the case of, say, that was 1 dimension, if we go up to 2 dimensions here, say a speaker. So this is a speaker where you're running just tones through it. We can see that's the same idea. What they've done is they've put a little sand on the speaker. And so this surface is now oscillating. It's having parts that are going up and parts that are going down. And the sand collects in the parts that are never up, right? So the parts that are just staying constant, whereas all the parts around them are going up and down. And so you can see these patterns of waves that show up on the speaker face. So the electrons that we were putting into orbits, right? That was like a ring around the atom. It's not quite an orbit, just an electron moving in that. Instead, it's a wave that fills it. It fills the entire orbital. So orbital is then going to be the designation for what the state of an electron is around an atom. It's like an orbit in the sense that it's kind of a region of space around the nucleus, but the electron fills the entire orbital and is a wave. And because the fact that it is a wave, that is what mandates quantization, because there's only certain configurations. You have to the electron has to double back on itself. So it can do that by going out and in 3 times or 4 times or 5 times or 6 times. But importantly, it can't do it 6.5 times or 4.2 times. It has to be an integer number. And that is why we have these quantized states of electrons around nucleuses. Importantly, do you want to note these lines that we see, right? These orange lines, they're already a kind of a model of what electrons look like. But the important thing is that the electron is a wave. It fills the entire orbital. It's not necessarily like some object that's following a wave pattern. It is the wave, and it's oscillating. It's going up and down, in and out, in and out.
Okay, 4 questions on participation 618. You want to find all 4 of those questions, get them answered, get those answers submitted over on Blackboard by Thursday the 18th. Also on Thursday the 18th, there's going to be a second test. I wouldn't recommend waiting to do the participation if you're watching this before the test. And also the heat effects pre-lab technique and notebook due at 9 a.m. Post-lab will be due for Saturday on that, and then we got the Module 6 homework due Saturday. There's no participation tomorrow because Juneteenth. So the only thing that's left is answers for the participation will go live Thursday night. Otherwise, that's it for the week. I hope you have a good weekend, have a good holiday. I'll see you next week, and take it easy. Bye-bye.